Ball of mass 0.2 kg is thrown vertically upwards with an initial velocity of 20 meter per second. Calculate the maximum potential energy it gains at as it goes up. So when the ball will go up, what will happen? It will have some initial kinetic energy here, which we can calculate. The V is given to us, the mass is given to us, and we can apply kinetic energy is equal to half mv square, and we can calculate as 40 joule. So this will be the kinetic energy when it is thrown up. The maximum value we can get when there is no friction. So if we assume that, so the potential energy it will gain at the top when whole of kinetic energy is converted into potential energy, that will be same 40 joules. So the maximum potential energy it can get is 40 joules. A stone of mass 500 gram is thrown vertically upwards with a velocity of 15 meter per second. Calculate the potential energy at the greatest height, so that the same logic which we applied, it will be the same to the kinetic energy at the bottom. B, the kinetic energy on reaching the ground. C, the total energy at its halfway point. So total energy, they mean mechanical energy, because the stone is only working under gravity, which is a conservative force. The mechanical energy will remain constant. So first we will check at the bottom where the stone was thrown. So the kinetic energy, we will apply this formula and we will calculate the energy this much. So what will happen? Let's go. As the stone goes up, this kinetic energy is converted into potential energy and entirely converted into potential energy as it reaches the greatest height. Thus, at the greatest height, the potential energy will be the same as it was having kinetic energy at the bottom. Now, when the stone reaches back, it will have same kinetic energy. We're assuming there is no friction, air, nothing like that. Then it will have the same kinetic energy as it was thrown with. So it will have the same answer here. So understand this point very clearly. It can't happen that if we throw a ball upwards, it'll come when it's coming downwards on our hands. It has increased speed. It has increased its speed. That cannot happen. You cannot generate energy. So whatever energy you are giving, that will come down back with us. If we are assuming there is no air friction, then okay, let's go. Question number 3. The metal ball of mass 2 kg is allowed to fall freely from the rest from a height of 5 meter above the ground. Take G is equal to 10. Calculate the potential energy possessed by the ball when initially at rest. So we can do uh, mg delta h. It's very simple. You can do it by yourself. B, what is the kinetic energy of the ball just before it hits the ground? So when it is just before hitting at this point, the kinetic energy will be what the potential energy it was having at the top. So the total potential energy, which was when it was at rest, is getting totally converted into kinetic energy when it is about to strike, right? When it strike, it changes. Let's see the next point. What happens to the mechanical energy after the ball hits the ground and comes to rest? Now what can happen is the mechanical energy can reduce, because see, there can be a loss of kinetic energy here in the form of sound, heat, due to the friction, due to change the shape of the floor. So that kind of factors will take the energy away. So it may rebound, or the floor is very muddy, it will just stay there. So the mechanical energy will, get converted into heat and sound energy. Okay, let's go question number 4. The diagram given below shows a sky jump. A skier weighs 60 kgs, stands at A at the top of sky jump. He moves A to B and takes off for his jump. So here is a skier, he comes like that and he takes off for jump. A, calculate the change in gravitational potential energy. So mg delta h, right? We have the formula, but what is the delta h here? So one thing we can do is, calculate the potential energy here, then calculate the potential energy here, and then subtract it. Or you can directly put what is the difference in height, right? 75 minus 15. So it will be 60. So you can directly apply that. That will be the potential energy difference here. So I'm just doing by in both ways, like P8A we calculated first. So this much PE at P at the lower point. See the potential energy less 9,000. Here it is 45,000. Now difference in potential energy or gravitational potential energy will be the difference of it. So that will be 45 minus 9, 36,000 joules, or 3.6 into 10 to the power 4 joules. So that way we can calculate difference. And as I was saying, alternatively, we can take delta H as 75 minus 16, 60. And difference in P can be given by that mg delta H. Putting this delta H of 60, we will get the same answer. So either way you can approach this question. Now let's see what is next. If 75% of the energy in part A becomes kinetic energy at B, calculate the speed at which the skier arrives at B. So now the change in potential energy is 36,000, right? But what he is saying is that out of this energy, some energy is going out. And how much is remaining? Uh, Yeah, only 75%. 75% only is becoming the kinetic energy, not the 100%. Ideally, it should be 100%. Like whole this energy, what is that difference in potential energy should be converted into kinetic energy. But that is not happening. Only 75% of it is getting converted into kinetic energy. So how much it is, we just need to multiply this as whole into 0.75. So we will see 75 as 0.75, multiply it. So here I've done this multiplication and you can get 27,000 joules. Now we know the kinetic energy will be this. This is the 75% of the total energy which was coming due to change in potential energy. So we will apply this kinetic energy. We have a formula because they are asking the speed. For that we are applying this. So kinetic energy, this kinetic energy has to be equal to half mv square. We'll put the values and we will solve, and it will give us plus minus 30 meter per second because it will be square root of this. If this square goes this way, then it will be 30 meter per second. We will report the positive value as speed will be positive 30 meter per second. Okay, let's go for the next question. A hydroelectric power station takes its water from the lake whose water level is 50 meter above the turbine. Assume an overall efficiency of 40%. Calculate the mass of water which must flow through the turbine each second to produce power output of 1 megawatt. Let's attempt this question. A hydroelectric power station takes its water from the lake whose water level is 50 meter above the turbine. Assuming an overall efficiency of 40%, calculate the mass of water which must flow through the turbine each second to produce the power output of 1 megawatt. 1 mega is 10 to the power 6. And G we have to take as 10 meter per second square. So here is a rough diagram. There is a lake here and water is coming down. It goes to water station and that moves some turbine and then we are creating electricity. So the height is given. Height is 50 meter. So the water will be coming, down 50 meters to the power station. Now we can approach one way is first let's see what is the power output we need. We need this much. 1 into 10 to the power 6 megawatt because mega means 10 to the power 6. But efficiency is 40% or in fraction if we say it is 0.4. So we know efficiency is equal to power output by power input. So we should know this formula that what efficiency stands for. Efficiency, it has this formula. We are showing it by eta. Now power input multiplied by eta should be equal to power output. I'm taking this side, that's why. So power input into 0.4 should be our power output. That is what we want. So that is what this much output we want. So we put it here. Now the power input will be, we will take this fraction down 0.4 and we will solve for this. So we will get this much. So this much should be the power input because the efficiency is less. See how much we are giving, but out of it we are only getting this 10^6 only. Why? Because 40% is getting reduced. So we need power input of this much. Now let's go forward. So it generates this much of power. Now let's see how this we can generate this much of power. This is the power input we need. This should come from the lake, right? This input we should get from the lake. So for generating this power, this much work should be done per second, right? That is what the power means. This much joules of work should be done per second. Power watt is nothing but joules per second. So now let m be the mass of water. Weight will be mg downwards. Due to this force, downward work will be done on the water by gravity. So what will happen, like let's say it is a m mass and it is coming down. So if it is having m here, the gravity will act on it. The force will be mg and this mass will come down with the energy, and that energy we are harnessing here. So we can calculate the work done mg into 50 into 1 because m we don't know. That is what we want to calculate, how much mass we need. Now the work done has to be equal to this, right? We need this much of input. So whatever work is done by this mass, that has to come through this mass. So we will equate this and we will solve for m and we'll get 5000 kg. So it's 5000 kg, we can get it like that. Okay. Now let's do the sixth question. A bob of simple pendulum is imparted a velocity of 5 meter per second when it is at its mean position. To what maximum vertical height will it rise on reaching its extreme position if 60% of its energy is lost in overcoming friction in air? In this case, they have told like we are losing some energy. So first, let's have like how much energy it has when it was at rest. So the mass of Bob is not given, but will not matter if you see this question. So here it will be the energy will be half mv square. Okay, so kinetic energy of the Bob will be half mv square, half m we don't know, so we will keep it like that, and we will square the 5 meter per second. 5 square is 25. Then we can calculate it is 25 by 2 m joules. Okay, so m we are just keeping as a variable. So the remaining energy which you will be having because there is this energy is getting lost, right? Maybe friction is here or due to air, right? So there's a friction. So what is happening, they are telling us that 60% of its energy is lost. So this kinetic energy 60% is lost. So how much is remaining? 40% is remaining, and 40% remaining means if we think in terms of fraction, only 0.4 times what it was is remaining. So zero point 0.4 we will multiply with the energy it was having initially. So we'll multiply this and we'll get 5 m joules. So as if now we got the remaining energy with which the bulb will go up. And this energy at the extreme position, what will happen? This kinetic energy will get converted into the potential energy. And this is the height they are asking. So we'll apply the formula of mgh and calculate that. Now, this as Bob reaches the extreme position, its kinetic energy is entirely converted into potential energy. So Fm is equal to mgh, and we'll first solve for h, and that we will get as 5 0.5 meter. So 0.5 will be the height of the Bob. So that is our answer.